All right, everyone. Hello, my name is Michael Sarullo, and for the past 6 weeks, I've worked as a scientific programming intern in the Wang Lab, where I developed a system that can use real-time phase extraction to study more about memory encoding in the hippocampus. So I'm going to go over some general concepts that we should know before understanding my work. First, I'll go over episodic memory and associated rhythms, the setup of my system, how I extracted phase from my waveform data, and how my results can help build a foundation for future studies pertaining to memory encoding in the hippocampus. So let's start with some background. At the surface level, episodic memory can be categorized as a recollection of a particular event that occurred in the past. Think back to a previous birthday or what you did for the 4th of July. Your recollection of these events is classified as episodic memory. Now, these memories are all encoded in the hippocampus of the brain as displayed in the graphic. Memory encoding simply refers to the conversion of your perception into some sort of form that can be easily stored in your brain for future storage. Think about it like this. If you want to take a t-shirt and put it into a closet, if you do that, it's just going to fall to the ground because gravity exists. So what you do instead is you put the shirt onto a hanger and then hang the shirt in the closet so that it's easy to store and retrieve whenever you need it. This is what happens in memory encoding. When you encode a memory, you allow it to be easily stored in the hippocampus and retrieved whenever it's needed. Now, I want to go further into the actual rhythms involved with memory encoding. So first, I want to show you this graphic right here. Right here, you can see entire rhythm right here. So a rhythm is comprised of multiple waves. One wavelength is basically one oscillation of a wave from trough to trough, or simply the bottom of a sinusoid. After that, or more specifically, we can look at the phase of a wave. The phase of the wave is exactly where you are on that wave. So in this case, I have another analogy. The rhythm can be compared to an entire ocean, with each wavelength being compared to a single wave in that ocean, and phase being a surfer on a certain wave. Now, there are many different types of waveforms emitted simultaneously from the hippocampus. And what we want to do here in the Wang Lab is first, I should go over that these waves at different frequencies can categorize function. And therefore, we want to specifically look into theta waves, which are waves from 6 to 10 hertz. And the reason why we're interested in these waves specifically is that they are theorized to have some sort of impact on memory encoding. So, why? Neuronal populations of the hippocampus are active at different phases of the theta cycle. And if we are able to target specific phases within the theta cycle using optogenetic stimulation, we can inhibit and activate different neuronal populations to see their effect on memory encoding. So how can we set up and execute a system that can determine phase? So here's the goal. We have to find a way to determine phase in real time so that we can actually see or apply stimulation to different parts of the hippocampus or certain phases of the theta rhythm. And this allows for us to activate and inhibit populations, as I mentioned previously. Now, I want to emphasize the real-time aspect. Since the waves come in really quickly, it's necessary to apply stimulation right when we see a certain phase. If we target the wrong phase, then we won't target the right populations. But now, instantaneous processing creates numerous different limitations for development. Every single algorithm had to be optimized, and every certain step that I could have taken in my program and my engineering had to have been taken. So here's the pipeline of data that I used. First, we have EEG or electroencephalogram data streaming in from a specimen, the hippocampus of a specimen. Then I use a microcontroller called the TNC 4.0, which I'll go over in my next slide, which basically takes in the input so I can use it in my program. Then I have my program written in the computer language C to process my input and to extract phase. Then once I target a specific phase, I will output a digital signal, which is on or off, in order to begin stimulation of different neuronal populations in the hippocampus. So let's discuss my setup. First, I use the microcontroller, the TNC 4.0. Here's a picture, and I actually have it right here. It's very small, very tiny, as suggested in the name. And the data is going to move in a closed loop fashion, meaning that the original EEG data comes from the hippocampus of the mouse, and my stimulation will end in the hippocampus of the mouse. And I use a programming language C for implementation and MATLAB for design. Now, I want to go a little more into this. MATLAB is optimized for mathematical and scientific processing. So it's very easy to program with, but since I need my program in real time, it was too slow for those purposes. So I had to switch gears and work only in C. Now, working in C was significantly harder, but I was able to get my processing speeds far quicker and actually meet my real-time requirement. So now let's get into how we actually process this data. So first, input data can be very unpredictable, as shown in this snippet of raw EEG data. As you can see, there are lots of different spikes and random oscillations that make it very, very hard to interpret. Now, how do we solve this? A bandpass filter can make it interpretable and also isolate only theta rhythms or rhythms of just 6 to 10 hertz from the general signal. This is comparable to having an orchestra and only wanting to isolate violins from that orchestra. And this is the result. Once we use our bandpass filter, we get a wave that is very smooth and almost looks like a sinusoid that is within 6 to 10 hertz. So now how do we extract phase? The Hilbert transform will allow us to do that. I won't get too far into that right now, but this is basically the output of the Hilbert transform. So as you can see, there is a light green sinusoid right here, which is our sample filter data. And then this dark green sawtooth pattern is our output for phase. Phase is measured from negative pi radians to pi radians, or just negative 180 degrees to 180 degrees, and tells you exactly where you are on that wave at the given moment. As you can see, at each trough, we begin at negative pi radians, and as we oscillate into the next trough, we get right back to where we started. So now, how do we close the loop? How can we actually target specific phases that we've extracted? So first, a scientist will predetermine what phase value they're interested in, of which my program will then begin to target. Once the phase is targeted, a signal will be emitted from my TNC 4.0 to begin optogenetic stimulation. Again, since phase changes so rapidly, it's really necessary to calculate phase within about 20 milliseconds, which is about a fraction of a blink of an eye, just for context. So we can ensure stimulation occurs at the right phase, therefore targeting the right neuronal populations. If the output signal occurs at the correct phase, then we can activate or inhibit on demand wherever we want in the hippocampus. So here is a graph depicting a sample signal with digital signals being emitted. On the left, I wanted to target phase at 0 radians. Just so you know, 0 radians occurs at the peak of every sinusoid. And as you can see, the light green, whenever we see a peak, we see a digital signal being emitted. And to test a different phase, I tested at phase pi over 2 radians, or 90 degrees, which is right in the middle of the descent of the sinusoid. So as you can see, in the middle of the descent, we see another digital signal being emitted, showing that my system appears to work. And here's the final system performance. The video should play, perfect. So this is how it actually looks in real time. So we have our original input, our extracted phase due to the bandpass filter and Hilbert transform. And then here I targeted the 0 radians phase. And as you can see, at every peak, we see an emitted signal. The processing time per entry was about 5 to 6 milliseconds as well, which is well within our bounds for real-time processing. So how can this system actually aid in future research? Well, first, observing the effects of phase-specific stimulation can identify certain associations between phase-specific neuronal activation and memory coding functions. For example, in this graphic that I have, associations could be drawn between the functions of some of these neuron populations and how memory encoding occurs. For example, if we feel that neuronal population yellow occurs or is active at phase negative pi, and the blue neuronal population is active at phase negative pi over 2, then we can target stimulation at these phases in order to see how these different populations affect memory encoding. And such results could serve as a basis, but not immediate treatment for understanding different memory-related diseases in the future. Finally, I'd like to definitely acknowledge some people. Raphael Hellman, who was my mentor throughout this entire project, helped me immensely. Before this presentation, I knew nothing about microcontrollers and signal processing, and he introduced all that to me. I'd like to thank Dr. Wang for letting me work in her lab, Dr. Lara Drago and Erica Eggerman for putting this beautiful program together and truly making it life-changing, my fellow interns and the MP5 supporters that made this program possible. Are there any questions?
I feel that if someone take something home from this is how the retrieval process of the memories work. I feel after your example of hanging the t-shirt, everyone will remember. So thank you for that.
What high school do you go to?
Oh, I attend Suncoast Community High School.
I know about you. You're waiting.
Early on in your presentation, you showed a progression of memories. And sometimes a situation where memories go away. And then is there a way to scientifically exhibit the restoration of memories? A condition, a medical condition, for example, that might cause memory and then the restoration over a period of time. Is there a way to measure that?
So I'm assuming you're asking if we can measure how memories can fade away or restore over time. So personally, in my research, I did not look specifically into storage over time of memory. I definitely think you could discuss it with my mentor afterwards. I mainly just focused with encoding memories, but yes, that is definitely a very interesting question now that I think about it. Yeah, I think if you wanted to, we could discuss with my mentor afterwards. Yeah, for sure.
Obviously, what you're doing is time critical because you're dealing with being at a certain phase of your waveform, and you use the microprocessor, and obviously you need C to be fast enough. What is if you would use a personal computer or any faster computer? Wouldn't that make it easier just to use simple programming rather than being forced to go to C or C++?
So the question was, would using a personal computer work more efficiently than using a microcontroller, right? So in this case, the reason why I used a microcontroller is due to the fact that in order to input a signal from a signal generator or from actual data, you actually need to have certain ports on the TNC itself that allow for the signal to come in. If I could have used a personal computer as my processor, I definitely would have, since it is, in my opinion, far faster than the TNC. But since my computer cannot actually take in analog input the way that we require in the lab, I had to use that certain processor. And pertaining to the programming language, in order to process, or in order to create a program for that processor, I had to use C. So yeah.
I'm going to hop in with a question from one of our Zoom viewers. What has this work inspired you to do next?
Oh, wow. Okay. So the question was, how does this project inspired, or what does this project inspire me to do next? I definitely want to look more into memory encoding. I've always been very concentrated in mathematics, computer science. So I think this project definitely opened me to an amazing application of math and computer science. I definitely want to pursue applying math and computer science to some sort of science in the future. And I think this project made me want to pursue applying it in neuroscience more than anywhere else. So yeah, I hope that answered the question.
Can you make me start crying before the coffee break?
I have two questions for you. One is the TNC 4.0 something that you developed? And the second is MATLAB code something that you incorporated into your final program or only something that you use as a preliminary step?
Sure. So to answer your first question, your first question was, did I develop the TNC myself? I did not develop the TNC myself, no, but everything that had to do with the TNC and like how it was programmed in how I input and output signals was done by me. And your other question was, did I use MATLAB did I use MATLAB in my final implementation or if I just use it as a design? So at first it was part of my final implementation, but over time I used it as a basis to copy, or not to copy, but to more mimic in C. So it serves as a baseline for the final implementation.
All right, I have to go to the other half of the dynamic duo.
You mentioned the Hilbert transform multiple times. How exactly does this transform work?
All right, thank you for asking.
Strap in, everybody.
It turns out I actually have a slide prepared for this. So the Hilbert transform is a series of different convolutions So basically, the Hilbert transform creates a different analytical signal that can be further manipulated. So as you can see here on the top left, we have a sample sinusoid. All right, and in order to perform the Hilbert transform, first what we're going to do is we're going to apply a Fourier transform, which will create a complex output. The complex output consists of a real and imaginary output. That's why it's complex. So what happens is this is plotted onto a plane. Then what we do once it's plotted onto the plane is we rotate these coefficients 90 degrees counterclockwise around the complex plane, around the origin. Then we can perform an inverse Fourier transform to get what we finally end up with in this graph right here. Once we have all these different points on this graph, what we can do is we can take the 4-quadrant inverse tangent, which simply what that is, it takes a certain point and the angle that it is away from the positive x-axis or real axis, since we're working in the complex plane. So once we get this angle, that is phase. Now, if we wanted to provide a vector instead, what we could do is we could use this formula right here. To take that, it would be the natural log of the unit vector of z divided by the imaginary number I. And as you can see, this is the output. And yes, that's basically how the Hilbert transform works. Are there any other questions?
Okay, I love math, so let's go for this. So you basically, if you want to determine the phase of your wave, you obviously have to determine what exactly the wavelength is, right?
Sure.
So to do that, you obviously, if you average more waves, you're gonna be more precise in determining what the wavelength is. But you risk that if the wave changes at all, like in speeds from 6 to 10 hertz, that you might miss it. So how did you determine how many waves you're gonna average over? Determine precisely the wavelength?
So that's a great question. So the question was, how do I determine how many waves are going to average in order to determine my phase, right? So here's the deal. I dealt more with frequency instead of wavelength in this case, but they're the inverse of each other, so it's pretty similar anyways. So essentially what I had to do in order to compute the transform, what I did was I changed the size of my buffer, which kind of housed a certain number of signals. And since it's between 6 to 10 hertz, it was kind of predictable to understand how many signals would be in the buffer at a given time. So I noticed that using my buffer, in order to determine a certain size, I had to figure out how to balance accuracy with processing time. And I found, personally, I don't know if this is getting too specific, but I used a buffer size of around 1,000 inputs at a time. And I found that that took in enough waves and allowed for accurate Hilbert transform in the end to allow for phase to not only come in quickly, but accurately. I used a first in, first out approach where a signal would come in, and then when a signal comes in, the signal at the front of an array would exit so that I could always begin processing the next phase value in real time. I hope that answered your question. Okay, perfect.